Hi, Assalamualaikum and hello to Dr. Arif. We are from Group 1, consists of me, Ahmad Afif Jazimin, Lim Kai Peng, Lau Jiro and Muhammad Nazri, of course, Thermodynamics and Mechanics of Material Laboratory. So today we are going to present our experiment seat, which is torsion of bar. The first part is introduction. The objective of this experiment to investigate the relationship between torque and the angle of twist of a circular cross-section bar and to determine the modulus of rigidity of materials. Then the scope. In this experiment, we use and utilize three different types of solid bars which are aluminum, steel and nylon. Then we apply a different scale of rotation in this experiment, which are 200 millimeters and 400 millimeters, with initial point set to 0 for three different solid bars. Then we apply loads on the three solid bars within the range of loads of 5 Newton to 40 Newton, and the last one, the angle due to the torsion called as angle of twist will be recorded.
I will present about the theory. Shearing strain gamma is measured by the change in the angles by the side of the elements, which is length of shaft multiplied by shearing strain equals to length from the center to any point in the circle of the shaft and multiplied by angle of twist. Then we rearrange to determine the shearing strain. It also follows that the shearing strain is maximum on the surface of the shaft, where the length from the center to any point in the circle of the shaft is equal to the radius of the shaft. Therefore, we could know that maximum shearing strain is equal to the radius of the shaft multiplied by angle of twist and divides by length of shaft. The case of a shaft of length L and a uniform cross-section of radius C subjected to a torque T at its free end. The angle of twist and maximum shearing strain are related as maximum gamma equals to C times phi divided by L. In the elastic range, the yield stress is not exceeded anywhere in the shaft. Hooke's law applies, and maximum gamma equals to maximum tau divided by G, and this also equals to T times C divided by J times G. Solving for 5, it shows that 5 is equals to T times L divided by G and J, where J is polar moment of inertia and G is the modulus of rigidity.
So this is our experimental setup. As we can see in the figure 1, we have three different solid bars, which are steel solid bar, aluminum solid bar and nylon rod solid bar. Then we have a digital vernier caliper to record the diameter of the solid bars. Then we have a screwdriver, ruler, mesh loads range of 5 Newton to 40 Newton, and the last one, torsion bars testing machine.
Step 1. Diameter of aluminum solid bar, steel solid bar and nylon solid bar were measured and recorded. Step 2. Steel solid bar was clamped in the position and load hanger was placed on the cord. Step 3. Rotation scale was adjusted to 200 millimeters from the fixed clamp and the pointer of machine was set to 0 degrees. Step 4. 5 Newton of load was added on the load hanger and the twist of load was recorded. Without changing the load, the rotation scale was adjusted to 400 millimeters from the fixed clamp and the angle of twist of the load was recorded as well. Step 6. Step 4 was repeated with the load weight of increment load of 5 Newton until the load achieved to 40 Newton and placed on the load hanger. Step 7. The experiment was repeated by replacing the steel solid bar with aluminum solid bar and nylon solid bar.
This is the data we obtained for the steel solid bar. This is the data we obtained for the aluminum solid bar. This is the data we obtained for the nylon solid bar. Note that the load we apply for nylon is different from the previous two solid bar since nylon cannot support a large weight load. In this experiment, one of our objectives is to find the modulus of rigidity. Before that, we need to find the polar moment of inertia by applying the formula J equals to pi over 2 times R power of 4. All the polar moment of inertia has shown as below. You may pause the video to go through the calculation. After we obtain the polar moment of inertia, we can now find the modulus of rigidity, which is denoted as G, to obtain a more accurate value of G. The formula is modified by substituting T equals to m times phi, where T is torque, phi is angle of twist, and m is the torsional stiffness. Due to the graph will be plotted later, hence the m is moved downward. The graphs shown below are the graph of angle of twist against torque for steel rod at 200mm and 400mm. You may pause the video to go through the graphs. The graphs shown below are the graph of angle of twist against torque for aluminium rod at 200mm and 400mm. Again, you may pause the video to go through the graphs. Lastly, these two graphs are the graph of angle of twist against torque for nylon rod at 200mm and 400mm. Based on the graphs we obtained previously, we can start finding the modulus of rigidity by substituting the values into the modified formula. The torsional stiffness m are obtained from the graphs. It is the gradient of the graph. You may pause the video to go through the calculation. Here are the calculation for G at L equals to 400mm. Note that there is an abnormal value we obtain. The reason will be briefly explained later. The calculation to obtain the value of G are the same as previous. The table shown below is the summary of polar moment of inertia and modulus of rigidity for each solid bar. Based on all the graphs, we observe that torque and twist of angle are directly proportional. When the torque increases, the twist of angle also increases until a certain limit where the solid bar is unable to support the weight load. The torque and twist formula is verified from the experiment. When L equals to 200mm, we observe that the steel bar has the lowest twist of angle, and the steel bar can support the highest weight load. When L equals to 400mm, we observe that the aluminium bar has the lowest twist of angle. However, this is an abnormal scenario, because suppose that steel bar should has the lowest twist of angle. This scenario occur is due to the steel bar didn't fix on the clamping point properly. This causes the torque is not distributed evenly across the material. Based on the table 5.4, the G decreased from steel solid bar to nylon. The type of material does not affect the G directly because J relies on the radius of the solid bar instead of the type of material. Although G is directly proportional to L based on the formula of G. However, L doesn't play a significant role affecting the G. In fact, when the L increases, the G decreases. This is because the L is a constant value throughout the experiment. Last but not least, throughout the experiment, we observe that when the J increases, the G decreases.
Next, I'll present about the conclusion. From the result obtained, we could know that when the torque increases, the twist of angle also increases. The steel solid bar has the highest of modulus of rigidity compared to aluminum and nylon. Polar moment of inertia J relies on the diameter or radius of the rod. The higher the diameter of the bar, the higher the J. To improve the inaccuracy of data obtained, firstly, we have to ensure the torque is distributed evenly across the material. Secondly, we have to repeat the experiment for several times. And lastly, make sure the solid bar is clamped properly at the end.
Safety procedures. Number 1, personal protective equipment PPE. Wear appropriate PPE such as lab coat and closed-toe shoe to prevent potential that might cause lots fallings. Number 2, handle the apparatus carefully. Handle the solid bars with care to avoid any injury Ensure the solid bars are securely clamped before placing the load hanger on the cord. Ensure the load hanger is empty when replacing the different material solid bars to prevent any accidents, and avoid to stand directly under the load hanger while it is being loaded and when adjusting the load. And the last one, report any injury. Report to lab assistant to get first aid treatment if there is any injury happens. This is our reference throughout this experiment.
This is our appendix, which are the data obtained during the experiment. Thank you for watching.